Sorry for the delay. Um, this is a regression model. Let me explain what is what. This is your dependent variable. T means time. This is dependent variable is for the ith individual, ith subject, measured at time 1, time 2, time 3, and so on. So forth. T is a time, I is a subject, numbers, for example. This is a constant term, and this variable x has 3 subscripts. One is I is the individual, okay? T is the time, and J is the variable. When you see here, if I deal with 5 variables, for example, covariates are gender, rural or urban, socioeconomic status, and so on. Therefore, it means that J number of variables can be put in the model. Usually, this is you don't need a regression model when you do a randomized controlled trial. Please remember that, because all the confounders are well balanced in randomized controlled trial. The regression analysis is needed for the observation studies, where you wanted to adjust for the confounders. This is to study the time effect. What does it mean? You would ask the question, what is the change in the y variable if there is a 1 unit change in your time? Say, for example, every month I follow up the patients. So I wanted to see if there is a 1 month change in my time variable, what is the corresponding change? In nephrology department, I said the ambulatory care, every 30 minutes you measure the BP values. Then you ask the question, what is the change in every 30 minutes? That is your time variable. So the time change in time, the regression, what is the change in time when there is 1 unit change in time is also important. Okay. And so this is the model. Both many times you see here, the covariates are measured over a period of time. So covariates are also measured over a period of time. So for example, if I say Y is a cholesterol variable, and this is a function of body fat is measured every time. Okay. But you don't do this for the gender or time independent variables. It doesn't change by time. So sometimes you can have height is changing, not height, weight is changing, body fat is changing, or it is something which is fixed and so on. So you need to decide how many such variables, time dependent variables, covariates. This is called time dependent covariates. Okay. Which means that as the Y variable changes, cholesterol varies, that covariates also changing. So therefore you need to do this. This is the model. Stuck. Stuck. Session 3. Session 3. Session 3. Really. Right. A1.
G1 session 3.
Okay. Okay. Before we go there, okay. Let me refresh you on a regression analysis first, and then both the regression, linear regression and logistic regression. Basically, the regression deals with the correlations. Correlation basically studying the pattern. The question is whether as one increases, other one increases or not. It is not just correlating two variables. We have a concept of one causes the other. We go with the concept of causation and then do the analysis. So these are all some simple examples. So this is basically the direction of the relationship and the extent of relationship. It's a positive correlation, or if there is a correlation exists, then what is a change as we change one variable in the dependent variable on the other variable. So usually we call it as association, means when you correlate two categorical variables. So for an example, gender and coronary heart disease, yes or no. We use the word, is there any association between the two, rather than saying, is there any correlation between the two? Usually we talk about if there's any correlation, but typically that is correlation is specifically used for continuous variables. So these are all the range. Please remember that the correlation range is from -1 to +1. So the R square is 0 to 1. Okay. Now the Y variable follows a normal distribution, and we are not going to see anything about non-normal now. This is very important. This is a positive correlation. And this, you know, what is negative correlation and what is no correlations and so on. So no correlation. This scatter plot is the step one diagram that you need to do to study the direction. And this is, it has twin purposes. The scatter plot, as I said, the binary univariate analysis and regression analysis. It serves two purposes. One is to see is there any, what is that kind of direction going on in the data. The next one is there any outlier in the data? Please remember, this is very important because the outlier is very sensitive to any regression analysis. Sometimes you see a scatter plot like this, which the linear is not suitable for this kind of diagram. So therefore, you would go for curve linear regression, especially gestational age and birth weight. It is not linear. It is after some time it gets flattened. It's a sigma shaped curve. So ideally, if we all do is just the linear regression analysis for gestational age and birth weight. Ideally speaking, you should do a quadratic term added into the linear regression model. So that is something which we will see. Let us not go into the details. So this is, if there is an outlier that causes big problem. If you wanted to have a very good regression analysis, put a couple of outliers in the model, you'll get a very high correlation and so on. I'm just joking, but this helps you to figure out what are kind of outliers are sitting there in the data. So just please go through this one. There is this outlier here. So therefore, you just see, you wanted to report it and delete it, and report it, and or you just edit your data and deal with that. So this is what we said, and these are all the purpose of doing regression analysis. Basically, we are interested in dealing with the confounding variables in the data and also derive regression equations. That is a prediction modeling concept in regression analysis. This is to adjust for confounding effect in epidemiology. This is the main purpose we have. Now let me go into interpreting the regression coefficients. There are two drugs used in animals. This is the blood pressure values. Drug B and drug A. Say, for example, if you take out the drug from the animals, what kind of blood pressure that animals will have? Any idea? Constant. So if drug becomes zero, that constant tells you that this is the baseline blood pressure that animals had. So as you add the drug, it increases as you increase your dose. Okay. Now, because the dose is different, but you see here, either drug A or drug B I use, if I remove the drug, they all come back to the normal blood pressure of 20. Is that okay? So that is a significance of dealing with constant term in regression analysis. What does it mean to us? It means a lot to epidemiology. Say, for example, if we say that if I remove cigarette smoking, alcoholism, completely the lung cancer or whatever cancer will be taken out from the community. Is that true? No, it is not. So basically the constant term tells you what is the baseline risk that everybody has, every community has. That is the use of constant term. Here today, that what we are saying, what do we say that, for example, in the drug B, drug A, the regression coefficient is B, 15. If 1 unit increase in your drug dose, 15 units change in your blood pressure. So if I increase the dose by 4 units, what kind of change happens in the regression? So that is a simple calculation which you do. Now, this is, just explaining this regression equation. These are all the assumptions which we have, that is independence. Observations are independent. But in repeated measures analysis, the observations are not independent. So we are violating the assumptions there. And homogeneity in variance. So what do we mean by homogeneity in variance? The y variable follows normal. Don't go for testing for normality and all that when you do regression analysis. It is nearly normal. Okay. We don't usually do any test to see, make sure that y follows normal. And similarly for the homozygosity or the homogeneity, yes. So the independence has to be satisfied. Okay, for example, I remember there was a outside obstetrician wanted to go for a Singapore conference. So nobody is there except CMC, she knows. She came to our department. She said she has got 500 observations of gestational age and birth weight of the babies, or sorry, biparietal diameter or something like that. So I said, how many women were studied? She said about 100 women or 90 women studied. So each woman has visited her 3 or 4 times. Okay, you understand? So now if you say I am a woman, I visited her 3 times. So I have 3 readings contributed, 3 gestational age and corresponding biparietal diameter. So therefore, shall I take this? She claimed that she has got 500 observations, but it is 90 women. Do you understand? Now you tell me whether am I dealing or is she dealing with independent observations or correlated observations? Correlated observations. Definitely today that you will not do that kind of simple regression analysis for the data. Okay, so that's something. And the normality is very important. It should not be very skewed or whatever. And the homogeneity and variance is, let me give you some examples. So there are indirect way of testing whether the data have equal variance across X variable that I'll tell you later on. So this is for a given variable, given X variable particular unit. If you look at the dependent variable, the distribution is normal. If you take 4 dose, all the responses are normal and have some kind of variance. All these variances are expected to be same. That is called homogeneity in variance. Oh, how do I do it? How do I test it? So you can do a test indirectly by looking at the residuals and so on. That is not necessary now. So we'll have a soft stand on this one. This is what I said. This is here. A woman come to. So this I explained to you, this estimated birth weight and so on and so forth, not independent observations. This is very important statistics called Wald test, t-test. So basically, Wald is a scientist who has found out this test. Standard error of the regression coefficient divided by, regression coefficient divided by standard error follows t distribution. Okay. So therefore, you need to see whenever you see any regression coefficient with standard error, and you look at the t statistics, and if it is greater than 1.96, that variable is statistically significant. Okay. This is Wald test. We call it as Wald test. So this is something which is not necessary. If we say it is not significant, does not mean that it is not significant. Probably the curvilinear relationship is modeled as a linear regression. Therefore, you did not find that as significant. Let us spend some time to understand this. Okay, this is analysis of variance statistics, the F statistics table. This is very important when you do regression analysis. Regression is one line which explains the variability, and that is this one. So therefore, the variability in the y variable, dependent variable, minus the error, sum of square due to error. Error is basically unexplained for a given model. And this is the residual variance. And this is whether that is significant as compared to this. Okay. The residual is basically chance variability, which can be reduced, but it cannot be completely eliminated. Please remember, that has to be there. If it is, unless you are R square, the performance of the model is very high, say 100% accurate, that it has to be zero. In ideal situation, it cannot be zero. If this becomes zero, your performance of the model is going to be very high. This is R square statistics. What is the variability due to regression divided by that, the variability of the dependent variable. So this is due to regression, and this is the variability of the y variable. The regression is able to explain 100% of your y variable, then the R square becomes 100%. Okay. This can happen, R square cannot be 100%. But animal studies like pharmacology, biochemistry, they do 6 animals, 5 animals. They're all grown in the same environment and so on. There you can get 60%, 70% R square. In the human being studies, you cannot get R square to 60%, 70% and all, unless the data has outliers. It's very difficult to get R square 20%, 30% in human being studies. So therefore, this is the R square is a very important statistics. It's called goodness of its statistics. In any conference or anywhere, if somebody presented R square is 80%, 90%, we don't trust the data. Okay. You should ask the question. If I do any analysis, if my R square is very poor, then I will not present it. Why should I present it? Why should I say it? But you should ask the question, what is your R square, to say whether I trust this model or not. So this is the multicollinearity is a very important concept. So for example, that is one of the reasons when you do we are talking about regression multivariable analysis today. So this can happen in your regression analysis. So this is the cycle, and this is from my PhD thesis. Okay, don't ask me my R square, you get upset to that. So this is, say for example, the area is rural or urban. This is the gravida number of pregnancies. So this is a cycle length. This rural women had almost 32 days, whereas urban women had 31 days cycle length. First of all, it is not 28 days. Okay. So therefore, you see similarly, when you look at this data, the parity, 32 days and 31 days. So there is a good correlation between parity and gravity. Do you agree with me? Do you see a good correlation between the two? They are all mimicking the same, whether you use rural gravida or parity. Okay, highly correlated data. I did the regression analysis. Now, someone has to interpret the gravida regression coefficient and parity regression coefficient. One unit change in your gravida, one more pregnancy in your life. How much change in the cycle length? 0.26 days change. So I would expect similar results in the parity as well. Do you agree with me? Because they're all similar, except the abortion. So the parity is saying negative correlation and the value is 0.3. What does it say? It says that as parity number of live births increases, the cycle length decreases and so on. So do you agree with this? My boss started laughing about this analysis. You wanted to know this is because that parity and gravida are highly correlated. Cholesterol and fat is highly correlated. If you run a regression with highly correlated two independent variables, you'll end up with this kind of results, which is confusing. Another thing, what you do not know is this kind of correlation, how much have they affected the other regression coefficients? You understand? So therefore, the multicollinearity is a big issue here. Usually this is assessed by many statistics, the case statistics and variance inflation factor and so on. See, for example, when all other variables were around 1 or 2, the gravity and parity had values 11 and 14. It tells you there is a strong correlation going on between these two variables and will affect your regression coefficients. Okay, so what is the solution? So now you have many methods to handle this. Now, this is the simplest one is after 2, which is more reliable. My boss said women may not remember the number of gravidas, number of pregnancies, because the prolonged menstruation or this thing was considered as a pregnancy. Therefore, drop pregnancies and take live births. So we did this analysis, but you see now what is the correlation which is going on here? Okay. Absolutely, there is no correlation. You just correlate this result with the graph which I had shown you. No correlation. So this is because of, I have not told you about, you need to eyeball the data of other regression coefficients, see how much change has happened in your data. Okay. This is the regression adjusted method. You see, this is coming in a different direction, but the parity has a similar effect. If you do regression adjusted analysis for collinearity. Look at this data and tell me what is happening here. This is, we had an outstanding epidemiologist, obstetrics gynecology department, Dr. Mathai Matthew. So this is about his studies dealing with the 900 women. This is about if the lady is a passive smoker, what kind of decline happens in her baby's birth weight. Do you understand? So if you have a covariate called the variable measured as she's a passive smoker, yes or no? Okay. So you need to see where is that variable, passive smoking, yes or no? What does this value? What does it tell you? Yeah, if I'm not passive smoker, 0. 1 means passive smoker. If you move from 0 to 1, there is a birth weight decline. Do you understand this? Decline in the birth weight, 62 grams reduces. So, which is significant also. I wanted you to look at gestation and gestation square. Are they not same? Say for now, are they not same or highly correlated? Say, for example, if your gestational age is 25 weeks, 25 weeks square is 625. So if you do the correlations, both will go together. The correlation will be highly significant, one almost. So why should we have gestation and gestation square in the analysis? It introduces multicollinearity. Why should we have GA and GA square? Yes, this is what I said. The gestational age and birth weight have a linear, not a linear relationship. It has got a quadratic relationship. Now what I'm trying to say is, this is, so you have to appropriately model it. Many times we don't do that. This is your, this is GA. This is what you get, the real life situation. If you do a linear regression analysis, you would land up with a curve like this. This is what the regression analysis says. If you put one variable GA versus birth weight. So when you put GA square, the GA square has a negative regression coefficient. What it does is, one allows you to go higher. Say, for example, like this, it will go here like this. The minus part will taper it down. So you get a curve like that. Do you understand? One is a positive correlation, it goes on like this. The other one is a negative correlation, means it will pull you down. So finally you get a quadratic shape. Therefore, when you have a curvilinear regression, you have to do the modeling like this. Is that right? Okay. Yes. Both should be there. GA square alone will have, I don't know, we'll have to try that out. What happens? Still, it is a linear. It is not curvilinear. It is going to be a linear. Okay. This is, okay. This is about the regression. People who have not attended earlier formal logistic regression classes, let me try to explain this. Why it is called logit. Okay. The framing I'm studying has contributed many statistical methods in science. One of the statistical methods is logistic regression analysis. The question raised was, if someone had a coronary heart disease, yes or no, how do we model it? Until that time, we had only one model, normal regression analysis. You cannot consider yes or no questions as a bivariate category outcome as continuous variable. And therefore, people started working on logistic regression analysis. So therefore, the outcome is binary. Now you can have many categories, ordinal, polycotomous, and so on. Mostly it is binary, okay? Cure or no cure. These are all the covariates which you have. Case or control in case control studies. This is your risk factors. Myocardial infarction, yes or no, risk factors. Outcome is binary. So for logistic regression analysis. Usually it is advised for you to have the bad event as 1 and the good event as 0. Okay, it's easy to interpret. So therefore, this is what now the models are the softwares are very sophisticated. You can say, this is my outcome, it will model automatically. But I would say, then just code it as 0 or 1 and do the analysis. This is called a logit model. The pharmacologists are very well aware of this one. This is called e power a plus bx. Scientists thought there's a plus bx, linear regression part is sitting there. except that E is in the base. So if you try to get rid of the E, then we will come back to regression analysis equation. Is that right? So this is the clue which they had. Therefore, they modeled it. What does it mean here? The probability of getting disease, bad outcome, okay, given the covariates. This is the model. Now you see, therefore, the complement is probability of not getting the disease. Is that right? We are talking in terms of probability, not like regression analysis, birth weight is the outcome variable, cholesterol is the outcome variable. So this is a probability, please remember. Y variable is a probability. Probability of getting the bad outcome given covariates. So the complement is probability of not getting the bad outcome given covariates. Therefore, 1 minus of that. Okay. The odd is defined as ratio of two probabilities. Probability of getting a bad outcome to the complement of it. Not any probabilities. One is complement to other. That is called odds of getting the bad outcome. That is E power A plus BX. Okay. How do I get rid of this E? Take logarithm, and this is the logarithm part of it. This is called a logit. So this part, log odds, is called a logit, which is a linear equation, A plus BX. Is that right? So how do I get rid of this? If we take, so this is, for an example, this is a sigmoidal curve, probabilities 0 to 1, 0 to 1, this is your X variable. This has the probability has a sigmoidal curve. When you take logarithmic change, and it becomes linear. Okay, let me skip some of the slides. So when you take E power of the regression coefficient, this is your regression. Do you remember I showed you the regression equation? This is your regression equation. You have mouse or something for this? So this is your regression equation. This is what we are saying regression coefficient. If you take anti-log of the regression coefficient, that gives you odds ratio. This is odds ratio. E power B is odds ratio. So in a logistic regression, what you have to do is whenever you get a regression coefficient, which you have seen earlier, if you take anti-logarithm of or exponentiation of that, that gives you the odds ratio. Okay, the interpretation is similar as 1 unit change from x-axis. What is the corresponding change in terms of odds? This is a multivariate scenario, like multiple regression analysis. We have the same concept. This is many times you see here, this is a scatter plot of the variable age and coronary heart disease. And this is, do you find any pattern evolved from this graph? It's very unclear. Is there any correlation between the two? But you see, you reorganize the data and present it, there is a sigmoidal curve. What does it say? As age increases, the probability of getting disease is increasing here. So therefore, many times that even though you deal with the continuous variable, which you think that you can handle it with the regression analysis, it is very appropriate to do logistic regression analysis. Okay, this is a regression coefficient. We are interested in the age. If you take E power of the 0.11, that will give you the odds ratio. Okay, 1 unit change in your age, what is the corresponding change in your odds? That is this thing. The log likelihood systems as statistics, which I don't want to go into detail about it. This is what we are going to use today and tomorrow. Log likelihood becomes smaller and smaller if the model prediction becomes better and better. Please remember the direction. This is basically O minus E concept. O is observed, E is expected. If the difference is smaller, the likelihood becomes smaller. The model is better. O is closer to E, then the model is better. The likelihood ratio statistics will come down. Please remember, this is what we are going to see now. Let me skip some of this part and we'll go into this. This is an important slide. I wanted you to look at it. This is about neonatal mortality per gram change. This is your question is what this is. Say, for example, what is your, in this analysis, neonatal mortality, yes or no, is your dependent variable. Is that right? And the calorie intake is in grams. Okay. Now, when you look at the regression coefficient, it says 0.000. Someone like to interpret this 0.001 for me. Or shall I ask you a question? Is it important to look at nutrient intake, calorie intake? Very small effect. Shall we throw it out? Calories are measured in grams. What is the interpretation? If 1 gram change in your calorie, what is the probability of getting disease? Has to be very, very tiny, isn't it? So therefore, the odds ratio has to be very, very small. We don't know whether it's an important effect or not. If I say there's a 500 gram change in your X variable, what is a corresponding change in your odds ratio? Then it makes sense, okay? So when I say this, say for example here, if there is 1,000 unit change in your X variable, there's a 50% reduction in your odds ratio. Because the regression coefficient is in minus, whenever you see the regression coefficient, logistic regression analysis as a negative value, it means it is protective. Odds ratio has to be much lower than 0. So 1. So this is 50% protection. So if you increase the intake by 1,000 grams more, there is a 50% reduction in your mortality. So therefore, whenever you see a small value of 0.000, something like that, you should ask how the X variable was measured. In grams or whatever is very tiny values, it has to be smaller. So you should not throw it out. And many people don't know about it. Still, you have to go back and teach your colleagues. These are all the dummy variables. So do you have any questions in the logistic regression analysis? Okay. Let us go into morning. I started off with the saying, the school example. When you do some adjustment, the regression coefficient, the standard error will come down drastically. It will become larger, and therefore it makes you insignificant values from the analysis. Do you remember what I said in the morning school example, 2 curriculums? Unadjusted analysis gave you 0.03 is significant, whereas adjusted analysis gave you something 0.18. Do you remember? Insignificant. That is meant for cross-sectional studies where the outcome is measured only once. And there is a cluster design or whatever. In that situation, please remember, let me explain the situation. We said we do a lot of community-based, cluster-based studies. So cross-sectional studies where outcome and exposure measured at the same time based on cluster design. In that situation, if you don't adjust for clustering, your standard error will be smaller, therefore you tend to give false positive results. If you do adjustment for the clustering, that significant becomes insignificant. Is that right? So this is the rule for cross-sectional cluster-based designs. We are going to see totally different concept if the exposure is or outcome is measured over a period of time. You will get the reverse results. Therefore, if you analyze it properly, say for example, the outcome was measured repeatedly. Covariate was measured repeatedly. And if you do the proper analysis, you have the chance to show significant results. If you ignore it, you lose your significance. You understand? Therefore, the regression, the standard error of the regression coefficients becomes smaller and smaller if you do GE analysis. Where do you use GE analysis? Only when there is a repeated measured data analysis. That situation, the situation is totally different. This is what you wanted to ask you. Yes, yeah. This is the model which I just explained just some time back. The cholesterol measured at 6 time points, body fatness measured at 6 time points. Okay. It's a repeated measures data analysis or longitudinal data analysis. Adjusted for gender and baseline fitness and smoking status. Now, there's a concept called population average model and random coefficient model. There are two models in the morning introduction I said. The G deals with population average model. What is population average model? Population average model is, we have been talking about the information is clustered, correlated, and so on. Grossly, if we say this is the kind of correlation structure which is going on, this is called a population average model. There are 4 or 5 correlation structures. You need to pick up one good correlation structure and do the analysis. Then it is called a population average model. But if you wanted to find out exactly what is the kind of correlation going on in unit, then it is called a subject-specific model. Tomorrow we are going to see multi-level modeling. That gives you exact amount of correlation which is going on between the doctors, between the medical institutions, and so on. Or between individuals, within the same individual, etc. So, okay. There are two kinds of concepts when you analyze repeated measures data analysis. As I said, say for example here that this example, cholesterol measured at 6 time points and body fatness is a covariate measured at 6 time points. How do I analyze it? The first concept, as I said in the morning, Johns Hopkins University people have come out with a model called GE, which is a population average model. What they did was very simple, easy to understand concept. Capture the correlation structure, not exact value. What do you see here? Correlation structure, because of 6 time points. Correlation structure. What is correlation structure? Over time, the correlation can become weakened, and therefore there's no correlation. It's called autocorrelation. Exchangeable correlation, whether it is measured at 3 months or 4 months, the correlation is going to be same. That is called exchangeable correlations. And so independent correlation structure, unstructured, and so on. You pick up what is relevant to your data by looking at the correlation structure and take that correlation, specify the correlation structure in your regression analysis. That is all you have to do. Okay. Then it becomes GE. If you try to do exactly how much is the correlation, I wanted to adjust for it, then it becomes multi-level modeling. Say for example, this example, I can do multi-level modeling because the individual, he contributed many data. Is that right? Say for example, tomorrow I will explain this to you in a bit. He contributed 6 readings. Is that right? Individual 2, 6 readings. And so on. What we are saying is, these readings are correlated. These readings are correlated. Therefore, we said this individual is a cluster. Is that right? Now, tomorrow we'll see some examples. Doctor 1, Doctor 2, he treats 10 patients. Okay, and he treats 10 patients. He's, for an example, he has gone abroad and come back. He knows the epidemiology very well, or treatment procedures very well. And therefore, the patient's responses are becoming better as compared to an MBBS doctor, for example. Or another person who is from the local area, he knows the epidemiology of that situation very well. So therefore, these doctors are called the clusters. So individual level, within mass below person, this is an obese person and so on. You understand? His observations are correlated. How do I analyze this data? Should I go for a population average model or should I go subject specific model? Either way you can approach it. Here, say for example, I can say here exchangeable correlation. Here I would say estimate intra-class correlation coefficient exactly and adjust for it. This is subject specific model. I'll tell you tomorrow, we'll see. You see the difference between the two. Okay. And so this is, the GE model is easy to address the risk factors. Here, you can do, if you have a good software, it is easy to do this kind of. What is the advantage of doing multi-level modeling? Say for an example here, if these two doctors are coming from a referral hospital and there are D4, D5, and so on, coming from a private clinic. So this, their experience is going to get transferred to the patients. You measure the patient's level here, and you deal with two levels now, doctor level and the institution level. The doctors are belonging to these institutions. The institutions are different. Therefore, you can bring in something else also. Okay. And so therefore, it is called a multi-level model. Any questions? So it is your responsibility to tire your levels. And then the rest is easy to bring in into the analysis. This is what we said, population average model and subject specific model. The GE, which is a population average model, this is what this heading says, working correlation structure. There are some specific structure, you deal with that. So this is your, we'll see, we are going to come in. Okay. So this is a regression model, and this is the correlation structure which goes into the model. Then the rest is easy. So once this science started coming, people started using this. Prior to that, we were using repeated measures for ANOVA and so on. That we are not going to cover. This is a very old technique, 20 years old technique. Still the pharmacologists use, because they can use, because they deal with a small number of observations and complete observations. Whereas in epidemiology, you deal with the real-time data, a lot of missing observations and so on and so forth. That the scenario is totally different. The correlation structure represents the correction for correlation between observations. Because once you correct this in the regression model, then the correlated observations becomes uncorrelated after the analysis, after the adjustment. It's like adjusting for your confounding variable. So therefore, we are dealing with between subject a significant beta 1 regression coefficient This is your covariate, fatness. It means either the people who have high levels of fat have also had high levels of cholesterol. It is a positive correlation. Okay. This is a population average model. So I say as compared to this is if I am a person with less body fat as compared to another person who is having a high level of body fat, that is you compare as compared to him, what is my level and so on and so forth. That is between subjective. Because it is a repeated measure, so you can say within subject, what was his level 1 month ahead or the baseline level? What is his level now after 6 months? So if you compare that within the subject, it's called within subjective interpretation. So therefore, the repeated measures data analysis, a population average model, it is meant to compare exposure, bad exposure value with the control values. So this is a iterative procedure, quasi likelihood. It's a likelihood I told you, difficult to estimate. So this is dependence is taken account of using within subject correlation, priori working correlation matrix. So this is a state output. Okay. This is your R output. This is what you are going to do today. Okay. As you see here, there is a regression coefficient. So linear regression analysis, outcome is cholesterol, independent variable is body fat. So the body fat is here. It's a positive. As the body fat increases, the cholesterol level increases. And that is very highly significant and so on. So these are all other covariates here. Morning I said, so you have to see if I don't do G analysis, what happens in my standard error? If I do G analysis, what happens in my standard error? That is what I yeah. So time interpretation. So this is between subject. I said two interpretation is possible between subjects, that one person compared to another person. And this is within subject, one time point for an individual as compared to other time point. Okay, that is within subject interpretations. So this is a very important concept. In general, ignoring the dependency of the observation will overestimate the standard error of the time dependent predictors. It's totally opposite to what we did in the morning. Morning we said if it is a cross-sectional study, if you measure the outcome and the exposure using a cluster design, it will give you a very wide standard error. If you adjust for it, it will give you the less, sorry, if you don't adjust for it, it will give you a smaller confidence standard error. If you adjust for it, it will give you a wider confidence interval, therefore less false positiveness. This is quite opposite to that. Now, this is your unadjusted standard error, regression standard error, 0.04. Here, this is 0.01. Body fat was not measured over a period of time. Okay. Therefore, this is one scenario. Another one is, so this is body fat is measured over a period of time. This is, therefore, this is, see here, 0.014, unadjusted regression analysis. And here it is 0.27. The variable baseline fitness is not measured over a period of time. So what happens in the standard error? Unadjusted is 0.14, adjusted is 0.27. It increased. I don't worry about it because this is not measured over a period of time. But you see here, body fat was measured over a period of time. Unadjusted regression value is how much? 0.04. Adjusted is how much? 0.01. So it decreases. Is that right? So today, as against the morning discussion, today we are saying that the adjusted analysis will give you a smaller standard error and gives you many significant results. Is that right? Please remember this. So there is an advantage if you do G analysis, you would be able to bring out a lot of significant results. Okay. The variable which is not measured over a period of time, that you don't worry about it. Okay. But if there is a repeated measures, there is an advantage of doing G analysis. This is to tell you the same thing again and again. This is about scale parameter. We are going to use, this is a scale parameter here. This is used to calculate R squared statistics. What is R squared, which we discussed a while ago. So calculate that to see, calculate your R squared statistics. Again, how good your GE model is by doing this analysis. This is what you have asked about this correlation structure. We'll come to this correlation structure. These are all the kind of correlation structures which we have. Independent, that is no correlation, naive analysis. There is no correlation going on. Exchangeable, this is what we use very much. Conservatively, this is the best correlation structure that studies have recommended. Autoregressive is a correlation structure over a period of time. If you do a study for 6 months versus 18 months, over a period of time, the correlation will weaken and the correlated observation disappears. Okay. That is autoregressive. Very rarely you find this kind of regression, autoregressive correlation. M dependent variables and unstructured. So this is independent, there's no correlation at all, as you see here. Over time, it's close to zero. Therefore, you say independent correlation structure. So you don't have to do a GE analysis when you have independent correlation structure. You can do a simple regression analysis. This is exchangeable point in time. Almost all any time point you see the correlations, they are nearly equal to other time point correlation, not exactly equal. So this is what M dependent. After 2 time points, so third time point is rho 2. After 2 time point, rho 3. I think it should be rho 2. So this is rho 2, and so on. So after certain time points, there is a correlation evolving. Therefore, this is called the M-dependent correlation structure. Autoregressive, this is going down. So when you put the power, the values will come down for a period of time. This is unstructured. You can't figure out what is happening in the correlation structure. Look at the data and tell me what kind of correlation going on here. Increasing or disappearing? Increasing, decreasing. Decreasing or increasing? If you are very confused, thoroughly confused, then put an exchangeable correlation structure. Please remember that is advice. So this is looks like nephrology data. This is look at this data and tell me what is the kind of correlation structure going on. Declining over a period of time, declining, but this here it increases. Sorry, increases or decreases? Decreases. So how do I figure out that when I'm confused to choose the best correlation structure? Any idea? How do you rate the model is good? Or if you wanted to compare two models, use likelihood ratio statistics. What is likelihood ratio statistics? It tells you the position of the model, how good the model is. That is likelihood ratio, meaning it is O minus A, observed data minus expected data from the expected is from the model. If they are closer to each other, that is the best model which you have. So you have two likelihood ratio statistics. Use one for, say for example, exchangeable correlation structure, autoregressive. You people have set a decreasing over a period of time, autoregressive, and compare the two values and see which is lower. The lower is the best model. So therefore, then you take that correlation structure and build the model. Shall I repeat it again? So you choose, doesn't matter, you choose a model, just a structure, put it in the model and get the likelihood ratio statistics. Say for example, likelihood ratio statistics is 200 for a model with the exchangeable correlation structure. A model with the autoregressive model correlation structure, it is 300. 200 versus 300. Which one is the best? 200 is the best. So exchangeable correlation structure is the best. So you can put each correlation structure and find out likelihood ratio statistics. Whichever is the minimum, you can get that model and run it. So said morning, conservatively, it is easy or choose. This is what this exercise is, using correlation structure and find out which is the best. Next one is, this is that exercise. This is exchangeable. This is a autoregressive model, and so on and so forth. This is what, if you have time, you can do this one. So long we have been talking about longitudinal studies. Typically, the meaning of longitudinal studies are repeated measures with the equal interval of time. So, but it doesn't have to be like that. Sometimes you measure the information for every month for 6 months and 9th month and 12th month. That you have an unequal number of intervals here. In that situation, how do you handle it? Okay. Code time as in actual values, not 1, 2, 3, 4, but so like 9 and 14. So now you would say that what is a 1 month increase in your t variable? What is a corresponding change in the regression coefficient? So this is very important. This is what about unequal space-time intervals. What we'll do is we'll do some problems. Now we'll discuss about it. Let me summarize what I have said. So we assume that observations are measured on equal time interval. Okay. And the outcome is measured on an equal time interval. If your covariate is also measured on an equal time interval, then how do you handle it? Now the question is, how do you choose a correlation structure? Okay. Conservatively, I would say exchangeable. When you write your methodology, you say we have used exchangeable correlation structure to analyze it. Any reviewer will understand that conservatively they have put. It is not easy to pick up. Otherwise, you'll have to put each correlation structure in the model and get the best out of it. That is what you'll have to do. So we have access to statisticians. It consumes less time only. Just change only that piece only and do it. Okay. Now, now we'll do practicals now, and then, or you wanted to have an early tea break and come back and do the practicals. And then we have binary analysis. This is for continuous variable. And we'll see binary outcomes. When you have repeated measures on binary outcomes, the theory is slightly different, and we'll do that one. So what you need to remember is someone claimed that he has done GE analysis. on repeated covariates, the standard error will be much lower as compared to unadjusted analysis. More likely to give significant results. You do the right analysis, that is your GE analysis. Is it okay? As compared to unadjusted analysis, and we don't worry too much about what happens in the time independent covariates, gender, and so on and so forth. So we don't care about it. So that is all I have to say. Please don't use ANOVA for repeated measures for epidemiological work. I'll tell you the problem. ANOVA for repeated measures is a multivariable technique. Morning multivariable technique, we said, if there is one missing observations, it excludes the whole case from the analysis. Okay. So people do this analysis using when they work in the lab because they have complete information, absolutely no problem. They will not have missing observations. But in epidemiology, we deal with a lot of missing observations. You lose your power. Cases are deleted from the analysis. It doesn't happen the GE analysis. If I don't have, say for example, 6 months data you have, if I don't have 2 months information, it adjusts the regression analysis, it adjusts for it. In other words, it estimates automatically inside. It's a linear concept. This cannot happen in your ANOVA for repeated measures. Okay. So it's good for lab people, but not good for others. Okay. So we'll stop here and then we'll have a tea and then come back. Is that okay? Do you have any questions? Yes.
What you said.
This is R squared from any epidemiological data, clinical data. Say for example, nephrology department data. R squared cannot be more than 20%, 30%. R squared. Even in your regression analysis, cannot exceed that much of correlations. That if there is an outlier in your data, it will shoot up to 40%, 50%, and so on, so forth. So if somebody says that he has got a very high value of 70%, 80%, you don't trust, maybe something wrong in the analysis. What could be wrong? I review some of the analysis by the pharmaceutical companies. Say for example, BMI is your dependent variable. BMI gets calculated how? Weight by height square. You put BMI here in the model and put weight also as one of the covariate in your independent variable. What will happen in your analysis? It is a part of the dependent variable. Therefore, your R square will shoot up like this. So you should realize that something wrong in the modeling. You have to find out what is wrong in the modeling, because that analysis would have been done by a very small person in the pharmaceutical industry who would not be aware of something like that. So therefore, we need to be aware that this can go wrong like this, or the data deals with the outlying values. Say for an example, we all deal with age. Age is not known, we'll put 99. That is how we deal with that, because right from the beginning, from our department, if something is missing, we'll put 99. If you analyze my data, which I coded, you would not know what is 99. You do the analysis, your R square will shoot up. So it's very difficult to find that out, but so you have to have some gross observation. You should ask more questions about it. Or yourself, even statisticians.
Because sometimes when we write, we make multiple models based on clinical and statistical significance. When we write the best model as per the goodness of fit is selected.
Yeah.
So we put like age, gender, BP, and in one model. Another model we use a different one and derive. Now we want to know which is the best model. So my understanding so far was whichever shows the highest R square, take that model.
That is correct. That is how we approach it. Regression analysis, the regression analysis then it doesn't deal with the likelihood ratio statistic. The logistic regression deals with the likelihood ratio statistic. The best model is based on the smaller likelihood ratio statistic. There are a lot of goodness of fit statistics. Hosmer and Lamshaw.
In logistic, I'm asking.
Logistic regression. Kashmir and Lamshaw, goodness of fit statistics. And Nahel Kerke, R square statistics. That I hope you use that.
Yeah. Yes.
So, and also you look at the likelihood ratio statistics as compared to other models and so on. Models are same with the same number of variables. If there is a difference, you learn that there is different variables in different models, then you look at likelihood ratio statistics. Otherwise, I don't see anything else. There are other methods. What kind of statistics you use?
Because we used to take that Nagelkar R square and take that from the various models, because we'll have clinically some models, some variates we'll think is significant, but might not have come up in univariate statistics.
You people use anything is different. My students use something else. I forgot the name of the goodness of its statistics. Logistic regression. Only
Hosmer will show the best goodness of it.
I remember Nehal Karkare because he's an Indian name, so therefore I like Nehal Karkare. There's one more statistics. That is a Hosmer and Lamshaw. Hosmer and Lamshaw statistics because of it. And this is R square. Nehal Karkare gives you R square. Yeah, Cox and Snell aspects. So another one using the residuals, you just look at the model as subjective.
This R square is different from the pseudo R square you're telling, or it is?
Same only.
Same only, right?
Yeah.
So then the one which has a higher R square value, is it still correct to take that model?
Correct.
Because mostly what we see is R square of 20, 22, 25, 30. You have to choose which model is better.
You will not get 80%, 90% or even 40% is very difficult to get.
Okay. But still it is statistically okay to use this model and say, because we are trying to say that 30% of the model is only explained by this model setup, whereas 70% is still at large. We cannot explain with this. Still we are okay that this modeling is robust.
No, my PhD thesis was on menstrual cycle length, which I presented the data. My R square 3%. I was very upset. With a lot of pull and push, we made it to 7%. So transformations and so on. The message is that the variables which my boss suggested did not work there. Something else. So you can't model it using this kind of variables. That is the fact. So other people will not waste their time like, why did that? So something. But we got good papers out of this. The one is this, it is not the variables which we have selected, nothing correlated with that the cycle length. Another one is that the collinearity problem. We've done extensive work on collinearity. My senior said, why are you breaking your head with the minus sign? Just remove the minus sign, everything will be okay. So we got a good paper in human biology and so on and so forth. So like that, so this is enough. So we'll have a break and then come back. Yes, sir, please. Minimum 2.
Is it fine with minimum 2 points also?
Yes. You can do the PAT t-test analysis. I'll recommend that Twisk. There's a book by Twisk. He has written 2 books. One is meant for multi-level modeling work. Very easy to read, very simple book. And there's another one for longitudinal data analysis. Twisk. I don't know his Peter full name. I don't know. Twisk. T-W-I-S-K. Twisk. So easy to read book. You can use it. And there are a lot of analysis. How do you use? You can do the PAT t-test analysis using G analysis. We can do that too.
Okay. And another question that I have is, for what percentage of missingness can we do GE? Is there any limit to that?
Now, my teacher was a very famous community medicine professor. He said, if you deal with 20% data, it's okay, do some imputations and all that. But if you deal with 30% missing observation, data is useless.
Okay.
And in randomized control trial, don't use the data if the missing is more than 10%. Because you have sophisticated missing data estimate procedures are available. Because you have those procedures, don't use it. Especially in a multi-level machine learning algorithms, there are better methods available to estimate the missing data. But the rule is that if it is more than 20% for observational studies, don't use it. So that is a concept.
Yes, sir. And
there is a book by Perspectives of Clinical Trials, Contemporary Perspectives of Clinical Trials, Peter Dorsey. It's a very big book for clinical trials. There are a lot of advice about missing data. But you should have time to read this.
yes, sir. Thank you, sir. And another question is, let's say the dependent variable we have at 5 different time points, and not all the independent variables we have for those 5 different time points. If it is present only for 3 time points, is it good to do GE or?
It's a good question. I have no idea about it. Maybe I would match that time points and correlate it with that.
Couldn't get you, sir.
If you have a Y variable, dependent variable measured for 5 time points, independent variable measured as a body fat measured for 3 time points, cholesterol measured for 5 time points, I would not consider the 2 time points data in the
omit the whole 2 time points data and do the
match that. If it is 135, here also 135, I consider that for the analysis. Do both and see what happens in your analysis. It should not make much difference.
Yes, sir. Thank you, sir.
So, with respect to anesthesia data, so let's say, sir, we are giving the anesthetic drug, like I'm measuring like around some 8 time points. The half-life of the drug is for till the 4 time points. So in this one, what kind of correlation structure should I choose?
What is the question here?
Like 8 time points is a measurement.
Correlation structure, I would say,
should I go
kind of sensitive analysis, I would look at each structure and take the best one in terms of likelihood issue.
Okay, so if can I go with autoregressive till the 4th order? Like,
then we can't combine both 2 methods.
Because the problem is that it is the half-life of the drug will be carried over only to the next 4 time points. So the last 4 time points will be like they won't be correlated at all. So is it better to choose autoregressive or something else?
Maybe you do exchangeable as well as autoregressive and see which is the best one.
Best, okay. And with respect to one more question is like unequal time distribution, like unequal time points measurement. So 1 month, 2 months are spaced equally. I can go with repeated measures ANOVA also. Simple repeated measures ANOVA also will do for equal time points between the fixed time interval, like one month only is there. But for GE, we can go with unequal time differences also. If which one is preferred, which GE or MLM?
I would go for today, I would go for GE. MLM both will give you same results.
Okay.
Everything is already modeling. That we'll see tomorrow. So I'm saying that if the question is whether ANOVA for repeated measures, anesthesia, you will not lose your patient, he is not going to run away, you'll have all the readings. And if you are comfortable with the ANOVA for repeated measures, we can do it, no problem. It has limitations in terms of interpretations. That other analysis will tell you whether this is significant or not. It will not give you the interpretations, like 1 unit change and things like that. Whether that variable is significant over time, interacted at the time, morning I said, is significant or not. So, but this will give you better interpretations. this analysis.
And examples which has been given, it is with respect to a single population, like only one population being measured at multiple time points. Let's say if it's an RCT, two different groups are there. So we need to put time into group interaction.
Yeah.
In the
Yes. So,
okay. Similar to what we do it in two-way repeated measures ANOVA.
Yeah, even in observational studies, if you have a very specific question measured, and you are going to do a GE analysis, adjusting for the confounders,
Okay.
I will do interaction analysis
Interaction.
to address
So that interaction effect answers my hypothesis.
Yes.
Thank you.
If we have many variables, like mornings, I said as a menstruation, we don't have any specific question. So exploratory analysis, that time we don't know what to put. So we understand, but if you have a specific question in your research, like for example, you would say you are interested in smoking alone, that is your intervention. The morning which he said two curriculums and things like that, measured over a period of time, then it is interaction with the smoking intervention.
Thank you.